Greetings to Dr. Ahmad, our evaluator. My name is Hariharan Raj, son of Munyadi, and my metric ID is MA17076. I am from Group 1, and the remaining names of my other group members have been put onto display for your viewing. And we are from section 02 of the subject BMM2543 Fluid Mechanics 2. And the reason for me to make this video is to make a presentation of the project that we have conducted for the past period of 5 weeks. So hope you enjoy the video. So as an introduction, the students who have enrolled for this course, namely BMM2543 Fluid Mechanics 2, have already been given a task to undergo and conduct a project which is to design and analyze a compressible flow through a converging and diverging duct. So the theory regarding this compressible flow topic, it can definitely be obtained in the book which is titled Fluid Mechanics Fundamentals and Applications, second edition, which is authored by Sir Eunice A. Chengel and Mr. John M. Kalimba. So in this project, we have set a few targets, which is to calculate the density, viscosity, specific heat capacity, universal gas constant, and also the specific heat constant for various types of fluids. So we have also showed the calculation and the plot of the graph for each result for each different type of fluid in our report. And according to this report, we had been divided into groups of 5 by the lecturer itself, and the project was given a period of 5 weeks to be completed. Moving on. Now I would like to explain about the objectives that we had before conducting and starting this project. So the first objective is to design and analyze a compressible flow through a converging diverging duct, as I have mentioned before. And the second objective is to calculate the stagnation, speed of sound, Mach number, and also the one-dimensional isentropic flow. And the third objective is to study the concept of stagnation state, speed of sound, Mach number, and also the one-dimensional isentropic flow for a compressible flow. Moving on. So now I would like to explain about what actually is a compressible flow. So to give you a rough idea on which type of real life applications or real life things actually use the concept of compressible flow, I have included the picture of a gas turbine and also the picture of a fighter jet. So these are a few examples. These are one of the many few examples that follow the concept of compressible flow. Moving on. So a compressible flow, or in other words, compressible flow can also be called as gas dynamics, is the branch of fluid mechanics that actually deals with flows of having significant changes in fluid density. While actually all flows are considered to be compressible, flows are usually treated as being incompressible when the Mach number is actually the ratio of the speed of the flow to the speed of sound. If this Mach number is actually smaller than 0.3, since the density change is due to the velocity, which is about 5% in that case, if this Mach number is smaller than 3, then that flow is considered to be incompressible. And the study of compressible flow is relevant to high-speed aircraft, jet engines, rocket motors, high-speed re-entry into planetary atmosphere, gas pipelines, commercial applications such as abrasive blasting, and many other fields. So the study of gas dynamics is often associated with the flight of modern high-speed aircraft and atmospheric re-entry of space exploration vehicles. Anyways, these origins all started with much more simpler machines. So at the beginning of the 19th century, investigation into the behavior of fired bullets led to improvement in the accuracy and capabilities of guns and artillery or weapons. And as the century progressed, inventors such as Gustav D. Level advanced the field, while researchers such as Ernst Mach he sought to understand the physical phenomena involved through experimentation. And at the beginning of the 20th century, the focus of gas dynamics research shifted to what would eventually now, at this date, it is called the aerospace industry. So that focus was actually shifting towards the aerospace industry in the beginning of the 20th century. So Ludwig Prandtl, the Prandtl number is named after him. And Ludwig Prandtl and some of his students actually proposed some important concepts ranging from the boundary layer to supersonic shock waves. supersonic wind tunnels, and also supersonic nozzle designs. And one of his famous students also, it's Theodor von Karman, a student of Prandtl, actually continued to improve the understanding of supersonic flow. There are many other notable figures in history, such as Mayer, Luigi Crocco, and Shapiro, who also contributed significantly to the principles considered fundamental to the study of modern gas dynamics or compressible flow. And many people have also contributed to this field. And accompanying the improved conceptual understanding of gas dynamics in the early 20th century was a public misconception that there existed a barrier to the attainable speed of aircraft, which is commonly referred to as the sound barrier. In truth, the barrier to supersonic flight was merely a technological one, although it was a stubborn barrier to overcome. And moving on. Now I would like to explain about the things which are involved in this compressible flow study. So the main five things I would say are stagnation, speed of sound, Mach number, one-dimensional isentropic flow, and also the converging and diverging ducts. So these are the main things which we need to understand and study before we can solve any issue which is regarding the incompressible flow. And now, from now on, my groupmate will take over. So thank you for hearing.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Lupah Hakim Ismail, MA11148. I will explain about part 2, which is the expected result and calculation. This part is divided by two parts, which is 2.1, the comparison of Mach number and pressure ratio simulation with the 1D calculation, and 2.2, which is the variation of density with the position X for one specific fluid type air. To calculate the Mach number, first we need to identify all the information given from the figure attached in the sample, which is D inlet is given equal to 0.2 meter, D at the throat equal to 0.15 meter, and D at outlet equal to 0.24 meter. Also show that length L1, which is the inlet toward the throat, equal to 0.3 meter, same as from the throat to the outlet, which is 0.3 meter. For make the calculation more easy to understand, I divided with two part, which is the nozzle part and the diffuser part. And formula using is area equal to pi d squared over 4. We use this formula because converging and diverging duct is in cylindrical shape. After that, we'll also use a formula area ratio shown in the slide. Next, for the example, at the point x equal to 0, which is the initial point, and the value of the k equal to 1.4, and then we can use the formula of the area to find the area at the point x, substitute the value of diameter, and then we get the area. And then we also find the area at the throat, substitute diameter at the throat, we get the area at the throat, and we find the ratio of the area at 1.777. After that, we can use the formula of area ratio by substituting the calculated area ratio and the value of k. We simplify the equation, and then we get Mach number at point x equal to 0.3587. After that, we can calculate the percentage of error, which is error equal to Mach number simulation minus Mach number isentropic or calculated over Mach number simulation, and then times with 100. We get 7.43 percentage of error at point x equal to 0. Next, there is some of special case where the diameter is not given. We need to find the diameter at the desired point, which is in this case the point x equal to 0.5 meter. So how to do it? We use trigonometry ratio. which is we're using sine, using formula sine to get the value of x, which is the opposite side, and then we get value x equal to 0.012543 meter. Must be noted that x not represent the total diameter, so we need to find the diameter at 0.045 meter by subtract the 0.2, which is the initial diameter, minus with 2 because there are two sides, and we get the diameter at 0.15 equal to 0.175 meter. And then later on we use the same formula for area and area star and area ratio. We get the answer by substituting the value we calculated. Here we get Mach number at point x 0.15 meter equal to 0.4879, and then we calculate the percentage of error and we get 0.18%. Next is the pressure ratio and percentage of error calculation. This is straight to the point because we just using the formula of the pressure ratio, P over P naught equal to 1 plus K minus 1 over 2 times with Mach number squared, powered by negative K over K minus 1. In this case, K is 1.4 and we at 0.0 meter, at 0.0, we use the calculated Mach number we calculated before, which is a 0.357A, and then we also we substitute all the information given into the equation, and then we get the answer is 0.9149. And then for the error we just pressure ratio simulation minus with pressure ratio isentropic or calculated, divide by pressure ratio simulation and times by 100, we get at point x equal to 0, the error percentage of error is 0.49%. As you can see, we have completed the table 2. This show the variation of the data, which is Mach number simulation, Mach number isentropic, and the percentage of the error of the Mach number isentropic, pressure ratio simulation, and the calculated pressure ratio 1D isentropic, and also the percentage of error. So based on the data, we can determine that from the calculation result shown in table 2 that the relationship between the Mach number simulation and Mach number calculation number is relatively similar. And then the value of Mach number simulation and calculation increase until it reached the end or outlet of the converging and diverging nozzle, which is 0.6 meter away. And the relationship between the pressure ratio simulation and pressure ratio calculation is nearly same value. And the pressure ratio is the pressure inside the convergent and divergent nozzle at each direction or position x mentioned in the table 2. The pressure ratio continuously decrease when the position or direction increase from the right of the convergent and the divergent nozzle. It means that pressure of the fluid keep on decrease in the nozzle. Next is the variation of density with position x for one specific fluid type that we chosen, which is air. The information given from the question is P naught is or stagnation pressure at inlet equal to 220 kPa, kilopascal, and T naught, temperature of stagnation temperature at inlet, given is 300 K, and R for air we use equal to 287 joule per kilogram Kelvin. And then we need to find the pressure at the desired point. At firstly, we need to find the density at the stagnation point by using formula P naught equal to density naught R times with T naught, and then we get the density is equal to 2.55 times 10 power negative 3 meter cube. After that, we can use the formula of density ratio. For example of the calculation, I choose at point X equal to 0.3 meter, and the value K is 1.4, and Mach number calculated equal to 1, and pressure ratio of the simulation equal to 0.5269. So the density, we need to find the density at the point X equals 0.3 meter by using the density ratio formula. We substitute all the value we get, and then we get the answer. The density at point X equal to 0.3 meter is 0.001614 kilogram per meter cube. From this table, we have chosen 5 different points, which is a 0 is initial point, 0.5, 0.15, 0.3 which is at the throat, 0.45 and 0.6 which is at the outlet. This is the density tabulated in the table. And then we have plot a graph of variation of density with position X for air. As we can see from the graph, the density of the air continues to drop from point X equal to 0 to 0.6 meter because the flow area reduced with decreasing pressure, and because the compressible flow of the air change its density with speed or Mach number. It's also important to note that the fluid Mach number continues to rise after passing through the neck, even though the flow area increased significantly in the area. And also, the continued decreasing in fluid density caused the increase in velocity when it passed the neck, and also with the decreasing in pressure and temperature. That's all for me. Thank you very much.
Okay. So for this part, we will talk about the effect of some parameters regardless of the flow properties. First, we will look at the parameters temperature versus X position. If we look at the table, we choose 5 position of X, which is 0.00, which is the entrance of the duct, 0.15, 0.3, 0.45, 0 and 0.6, which is the end of the duct. From the table, we can see that the gap difference between all 4 types of fluid, which is air, helium, carbon dioxide and hydrogen, was not much at the start. But at 0.6 meter, which is the end of the duct, there is a big gap between helium, which has 101.989 Kelvin, which is the lowest at the end of the duct, which is the lowest temperature at the end of the duct, and carbon dioxide, which has 163.194 Kelvin, which is the highest temperature at the end of the duct. We can see this more clearly from the graph. From 0 to 0.15, there is not much difference in temperature change of all 4 of fluid. Then the decreasing of the temperature of the fluid started to improve from 0.5 until 0.45. The acceleration of the temperature change started to worn off once it reached the outlet part of the duct, which is 0.5 until 0.6 meter. From the graph, we can conclude that helium is the most drastic in change of the temperature throughout the event. Next, we will look to the pressure difference between all four types of fluid versus X position. We use the same X position as the previous parameter, which is 0, 0.15, 0.3, 0.45 and 0.6. If we look at the difference of pressure between all four types of fluid throughout the event, they are pretty close from the beginning until the end. To make it more easier to understand, we can look at the graph. The line in the graph which represent each type of fluid move along close to each other from 0 to 0.6 meter. This means there is not much difference in pressure change between all four fluids throughout the event. The pattern of line movement in the graph from pressure graph and temperature graph is quite similar. It started sloping slowly from 0 to 0.15, then drastically from 0.15 to 0.45, then it slowed down at 0.45 to 0.6. The third parameter that had been calculated is velocity. We also use the same 5 position of X for this calculation. If we look at the table, the change of velocity throughout the event for air and carbon dioxide was not much different. We can see this more clearly from the graph. All four types of fluids velocity from 0 meter to 0.15 was only negligible. Then, the velocity started to increase from 0.15 meter to 0.5 meter and decreased drastically once they reached 0.45 meter until 0.6 meter. From this graph, we can find that hydrogen is the highest in change of velocity compared to other three fluids.
Hello, my name is Muhammad Ariskan Nabi Musaidi. My metric number is BMM2543. So I will present about temperature versus position for different inlet pressure, and velocity versus position for different inlet pressure. First, we will see the this formula: P over P naught equal to 1 plus K minus 1 over 2 multiplied by MA square the power of minus K over K minus 1. So this is the result. We got the MA for the different pressure for 2.205 kilopascal. Next, we will find the T. This is the calculation. Okay. Next, we will find the velocity. We will find the C first. C equal to square root K RT, and then we will continue with the next formula, which is MA equal to CV. So we get the first V 962 millisecond. So we will continue calculation with the different position x, which is 0.15, 0.3, 0.45, and 0.6 with different P inlet 210 kilopascal and 215 kilopascal. Okay, next we will see the graph temperature versus position x. The graph temperature versus position x shows that the temperature varies depending on the intake pressure. It reveals that the temperature has influenced the pressure inlet. The graph indicates a slight drop, which is due to the fact that as pressure inlet increase, the temperature decrease. Next is velocity versus position. According to the graph velocity versus position x, various input pressure have distinct effects on velocity. The graph depicts the relationship between velocity and pressure. The graph indicates a minor decrease in the curve. This can happen when the temperature drop and the velocity drop as well. When air flow through a converging diverging duct, the graph's connection may be expressed as a change in input pressure. That's all from me. Thank you.